All right, in our last discussion, we talked about the law of reflection, and it was kind of boring, right? Light comes in at some incident angle, and then it goes out at some reflected angle. This problem could be more interesting if we didn't use a flat surface where all the rays bounce off the same way, right? Yes, this is very boring. But what if we had a different situation where the surface was curved? Now that's interesting because the normal line is perpendicular to the tangent, but the tangent is always changing. So our normal line varies. And that means if we have a ray that comes in, it'll bounce off at various angles, and they're not necessarily the same angle. So we should explore this in a lot more detail. I've already kind of done some setup. I've kind of hand-waved this demo away and never actually done it formally, so this will be the first time, and we'll see if it works. Before we do that too much, we'll need to figure out some scheme for determining kind of a reflected or a reflected angle. So let's go back to, actually this one would be good. No, it won't. Let's go back to this picture. And let's say here I've got some kind of an angle. So this ray comes in and it makes some angle here with a line that we'll just call normal. So how would I get from this slope to that one? I would have to add something to it. So this slope has a rise over a run, and let's do this completely properly. I get 1, 2, 3, 4, 5, 6. So here's a run of 6, and 1, 2, 3, 4, 5, 6, 7, 8, 9. Oh, let's round off and say that's 10. The rise of negative 10, right? So that's the slope. So in this situation, what do we want to do? I want to make this slope, damn it, that won't work. The math ends up being infinity, so that's bad. Okay, let's try this again. I want to take this ray and I want to copy the angle that we have here. And that pretty much means make another version up there. So I'm kind of leading toward this law of reflection. Let's do this again. I need a slope, right? So here's a triangle. And it's got a run of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 16. And a rise of 1, 2, 3, 4, 5, 6, 7. So the slope of this line is, of course, the rise over the run, which is 7 over 16. First thing I need to do is figure out, how do I turn this line into that line? And I'm asking, what do we need to do to the slope? What do we need to add? So what is delta m such that we get our new slope? And our new slope is, of course, 0. So I need to do something to this slope to change it. So if I want to go from slope final, 0, minus slope initial, 7/16, that's the change. I need to add, or I guess in this case subtract, 7/16 as my slope in order to flatten this curve and make this, not this line, but that one. Okay, so big deal. This change gave us this angular change. So if we want to do that again here, I need to do this again, right? Do it twice. So now my new slope was 0. I want to take this away from it. I need a slope of negative 7/16 that ends here. So that would be 16 over. And I need to drop 7. So my initial position needs to be 1, 2, 3, 4, 5, 6, 7 up here. And that gives me this line. And what do you know? That is exactly the same angle as the one here. So we just developed a mathematical tool to help us kind of bisect these angles and copy them across the normal. So why is that relevant? Because we're working now with spherical mirrors, and I've already kind of traced a sphere, or in this case a circle, so this soda lid. And I found this radius and just kind of plotted everything out. So I want to do the same kind of thing where we intersect with a normal line, do this crazy math we did, and then try to find where is the new reflected ray. So, oh, it looks like I didn't bring my straight edge. Okay, so what we want to do is just send a ray in, have it intersect with this, and then do the reflection according to what we just did. I want to pick a spot that intersects exactly with one of the boxes. So this one looks good. So let's make this our incident ray. It comes in and it strikes the surface. How do we define the normal line? The normal has to be perpendicular to the tangent. And on anything like a circle, the tangent is, of course, tangent, but the perpendicular line ends up being radial. So it goes directly through the radius. And we know that any line from the radius should hit the surface at a perpendicular angle. So why don't we do this, and I'll leave it kind of dotted to let us know that this isn't a real ray, it's just a reference mark. And here we go. Here is some angle. And I need the output to be the same as this input, according to the law of reflection. So this is very doable. What was our scheme? We needed to find the rise over run. So here's a line, and I need to go to this new line. So we've got a run of, let's see, 1, 2, 3, 4, 5, 6, 7, 8. And a rise, or rather a fall, of 1, 2, 3, 4, 5, 6, 7. So if we wanted to do that again, we can see you're just going to change the numerator by a factor of 2. So 1, 2, 3, 4, 5, 6, 7. The denominator stayed unchanged. And we get something that looks like this. So that's an outgoing ray. It might be nice for us to kind of color this in to distinguish it from some new ray. So when we do this again, whoops. Okay, not great. I can also see just visually something about this doesn't quite look right. These angles don't look like they're exactly the same. So there looks like there has been some kind of a problem in this case. Oh well, we'll try it again. Here's a mark here. Looks good. If we come in, I need some kind of a normal line with a measurable slope. Okay. And then again, find the slope and double it. So that's a fall of 4. I already know how this is going to work out, right? 1, 2, 3, 4. And then we will connect the dots and see what comes out of it. All right. Let's make this one blue. And predictably, this demo didn't work out the way I thought it would, or the way I wanted it to. And I think I know the reason why, and I kind of suspected when we started. I was hoping that all of these incident rays, and you've learned about this in class hopefully, they should intersect at some point along this middle axis. And that creates what we call the focal point. So here we have what looks like an image is forming, but for parallel rays, the image should be at exactly the focal point, which should be right in the middle of these two. The reality is when we do these kinds of demonstrations or whatever with real mirrors, it turns out that you don't have a single focal point. You have a range. So here's the focal range for all of visible light in this particular problem. And what causes a focal range is something, or not visible light, just any wavelength. So what causes this to be a range instead of a point is a defect or an aberration. And this one is called spherical aberration. That might just be a single R. And it just fouls the image, right? So you have various focal ranges as you do it. That's a problem, I think, that turned up in one of the lab demos. We tried to make a nice image of a faraway object onto a screen, and it just kind of sucked because the mirrors were too curved. So this is a real thing that happens, and it can be combated by doing parabolic dishes instead of spherical ones. It kind of helps correct and bring all these to the focal point. So if you have a satellite dish, it's a parabolic, not a spherical dish, just because of this effect. This screws up your reception. So what is the deal with aberration, and why do we ignore it in all of our equations? You may have heard this is the thin mirror formula or the thin lens equation. And when we make the approximation that things are thin, we assume everything happens according to this plane. Right, so there is some curvature here, but really when you draw the ray diagrams, when you do any of the calculations, where exactly on the mirror it is, doesn't matter. You assume everything happens based on this point at the middle of the mirror. So let's just vent a radius of curvature, and let's make one a little bit big enough to where we can easily work with it. How about 5 and 5, make it 10? Is that 10? Bah, let's go 1, 2, 3, 4, 5. Let's go out to, nope. 1, 2, 3, 4, 5. Let's go to 20. So this will define as the radius of curvature for this mirror. And I want to do the same kind of stunt that we did before. Let's pick a location to send the rays into and see how do they reflect out. So in this case, my incoming ray 1 doesn't stop at the mirror. Make it go all the way to the plane. And then we'll send it through the radius to give us that normal line. And what was the trick we were doing before to copy this angle for the law of reflection? I wanted to take this and double it to the other side. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 11. And let's lower it. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So this should be our new ray. And these actually look a little bit more accurate than they did the first time. So we'll shade them in so we can do this again. All right, how about one more time? I want to come in from a little bit lower. We want to go through that point again. And then we want to double this. I guess that would be down here from 3 to 6. Now this is very interesting because both of these went through the same point when they reflected back. And I picked 2 arbitrary points with no consideration for, making this work. So if you want to do a third one, fine. We'll do a third one just to make sure I didn't get lucky. Here's one. How far up? 1, 2, 3, 4, 5, 7. So ray comes in at 7, and then 1, 2, 3, 4, 5, 6, 7. Hey. How about that? This one also reflected through this point. So the key issue for this is we want to make it a thin mirror. So one that doesn't have too much curvature, or if it's got a lot of curvature, all the action is happening here close to the center where it's flat. And we see all of these rays come through the same point. And this is the point that we want to call the focal point. It's where all the rays come to a focus. And what else can we say about it? Its distance is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this is 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. How about that? Apparently, the focal point for a mirror, assuming that it's thin, is 1/2 of the radius. So the key assumption was it's thin. We don't have to worry about the exact surface geometry, because when we do, it offsets these interactions away from this point, and it kind of shifts all of their focal points a little bit out or in based on how far away they are from the middle. So this equation, now we know where it came from.